Welcome everyone to a video on debugging. This is something I've covered loosely in some of my videos. However, I've never really covered it in enough detail that I feel like I've done it justice. And even this video is going to be, kind of like I usually do, kind of a paraphrasal of things. But if I were to actually take all the times when I was making the videos for this channel and not edit them, there would be a lot of me cussing and getting pissed off at things going wrong. So a part of me kind of feels like I convey programming to be a little bit easier than it really is. Even when making really simple examples and like small scale games for this channel, I'll still get things wrong and I'll still screw things up and get pissed off and have to edit out me cussing, trying to figure out what small little detail I missed. It's just inevitable that when you're working at a low level, such as you do when you're using languages like C and C++, that things are going to go wrong and your program is going to go down and crash. So let me just kind of go over some of the ways that can happen, and then I'll kind of talk about how the debugger works, how to wield it as a tool, and how to use it to get to the bottom of some of these. So arithmetic errors as far as dividing by zero. That's actually really uncommon, but I figured I'd put it here because it actually happened to me while preparing the materials for this video, and I'm like, are you serious? Dereferencing null pointers is a big way to crash your program. Accessing memory that doesn't belong to you, and there's many ways to do that, but the most common ways are, dereferencing a wild pointer or accessing outside of the bounds of a C array, which is basically equivalent of accessing memory that doesn't belong to you, because C arrays are just nothing more than blocks of memory. Runtime aborts, which are things like uncaught exceptions in C++, failed assertions, runtime checks that might be built into C++ classes that check for you to do things that you shouldn't, and so forth and so forth. So let's talk about the debugger a little bit. I've opened up a project that I've made, a simple game, in Xcode. And before we get into anything that can go wrong, I just want to explain essentially how the debugger works, what you can do with it. The debugger really doesn't come into play unless your program is stopped, either forcefully by the OS due to a crash or some kind of serious problem, or whether you stop it yourself by using a breakpoint. With the exception of those two scenarios, the debugger is more or less running in the background, not doing much. But I'm going to show you guys the second scenario where you actually purposely place a breakpoint and stop the program on purpose. So in this case, I've created a breakpoint right here at this SDL init line, and I'm going to run my program and ask it to essentially try to start. And what you'll see happens is the program starts, and immediately it says that thread 1, which is the only thread in the program, is at a breakpoint. And that basically means our program is stopped and we are essentially within the debugger. So what information is presented to us when we are stopped in the debugger? The first thing you'll notice is on the left you will be given essentially what's called a backtrace, or the call stack, which is essentially exactly where the program is paused in its execution. So what you'll basically see here is all the way down to int main, where we are with respect to which functions main has called, drilling all the way down to where we are. So in the case of main, we see, yes, we were in this line of main. Main called the constructor of the game loop via the smart pointer make shared function, and eventually we end up in here as we would expect. So we are paused essentially. So now that we've covered the call stack, I'd like to cover essentially how to see the value of variables once you're stopped. So every variable that is currently accessible or not initialized, or I should say not set yet, can be printed out via the debugger for us to actually see what's inside of it. There's a couple ways to do that. One way would just be to hover over the variables in Xcode to see essentially what they contain. Or if you're more kind of old-fashioned like me, you might want to use the terminal down here. I like to use the P command to just print them out, and it'll basically tell me what the contents of the arguments that I'm asking it to print out are. In this case, there's two null pointers here, which is for window and render, which is what I would expect because they haven't been created yet. There's actually a lot of commands you can type here that Xcode can do for you. For example, if you want to look at this backtrace that I just showed you here, you can just type BT, However, this is a lot uglier and harder to decipher versus the stuff on the left here. So it depends on how you want to use it, but a lot of the stuff I'm going to show you today, as far as printing out variables and kind of getting to the bottom of things, is going to be, I'm going to be using the terminal in the bottom. Another thing you'll notice here is that there's some really crappily designed icons by Apple as far as what you can do as far as stepping through the program. Stepping in a debugger is a way for you to essentially advance to the next line of code. There are two ways to step. One is to step over, meaning that you want to go to the very next line in this function, and then the other way is to step into, which means you want to actually descend into the function of whose line you're on and go inside of it and see what's going on. Because these are SDL functions and we don't have their source code, we're going to go ahead and step over here. So as you can see, SDL was initialized, a window was created. You'll notice this breakpoint is still here, but the actual part where the code is, current execution line, is moved as we step. So stepping the next line should take us down to here to the creation of the renderer, which it's done. And we step again. And then we step. So this is essentially how you step. I'm going to remove this breakpoint. So you guys get the idea. As you continue to step through things, you'll see that you can print out variables and now they'll have valid values as one would expect. So as you can see, this is pretty much the same scenario as before, except instead of being stopped by a breakpoint, the OS has stopped our program because essentially it crashed. One of the telltale signs that we've crashed is that you see basically bad access here and that the address is 0. That address is not always a valid thing to kind of tell you what went wrong, but whenever you see the address as 0 next to bad access, it's almost always a guaranteed telltale sign that you've crashed because you've dereferenced a null pointer. If you see really low values of address, like 0x0, or 10, or 12, or 16, that usually means you're really close to dereferencing a null pointer, or a struct that's set to null. In this case, it should be pretty obvious from those that have written in C before exactly why we've crashed here. Essentially, I've put in this really stupid 2 lines of code where I've created a C string, I've set it to null, and then I've tried to copy into it with a string literal. And of course, because this memory is essentially set to nothing valid or null, it will crash when it gets to this line. So let's get into a more tricky situation. I've essentially deleted this code because it really wasn't serving any purpose for the game, and I'm going to run it again. All right. Now we've landed in a different place in the program, but the basic situation is the same. The program has crashed. In this case, we actually have not necessarily any kind of memory crash, but sig abort, which means that the program has been aborted on purpose. That usually is some kind of failed runtime check, and in this case, since we can see we're in the middle of really ugly-looking template code, it stands to reason that we have crashed inside the C++ standard library due to some kind of a failed runtime check. You could try deciphering the stuff inside this template code. Usually it scares the hell out of people the first time they see it, and this is one of the reasons why people think C++ is so hard, because when something goes wrong, a lot of times you'll see really ugly template code like this. Typically what happens in this case is I just calmly move the call stack back into my userland code to see what's the most recent line that I wrote that caused the crash, and then it becomes less scary. So in this case, let's try to figure out what's going on. You can kind of think of this like a puzzle you're trying to solve. Whenever there are crashes and I'm not stressed out and under some kind of deadline, I kind of feel like debugging crashes is like solving a puzzle, like in a game like Zelda, because your brain really works the same way. It's kind of an interesting way to think about it, but it can be kind of fun. Almost like you're solving a puzzle in a game. It's not always straightforward what the answer is. And the more your career advances and the longer you've been coding, the more crazy puzzles you'll be able to solve. Where in the beginning, you'll really only understand how to recognize simple problems. So in this particular case, it looks like we've crashed at this line. The first thing I would probably want to do here is look at the arguments that I've passed to this function to see if they're valid. So the first thing I'm going to do is I'm going to print out tile bitmap names sub I. And what this is telling me here is that it's an empty string, but those ... periods at the end have me a little bit concerned that maybe this is not valid memory at this location. So I'm going to print out I. Now it says I is 3 here. And then I'm going to print out tile bitmap names all together. And immediately we can see this is an array of 2 strings. So we cannot access the third element, or the fourth element, I being 3, of an array that only contains 2. So in this case, it's very obvious to me that we have actually accidentally accessed past the bounds of an array. This could crash in a multitude of ways, but in this particular way, it's crashing because essentially the C++ string constructor is trying to initialize based off of something that doesn't exist. So one of the ways to take care of this would be to put a 2 in here. You can tell I was lazy when I wrote this code. And if you put a 2 in here, it should be pretty obvious. The compiler will probably tell you with a warning that you're accessing outside the end. In this case, it didn't, so it's even more scary. But I have a constant here in my class, which I have set to num tile bitmaps, which essentially is defined as 2, and it will no longer go past the bounds. So that'll fix this crash. So we're going to move right on. Okay, so what's going on here? Looks like the same crash that we had before with the string. It's bad access, code is 1, address is 0x0. So let's see what's going on with player. It looks like player is null, so we cannot use the arrow, which is a dereferencing, to call a method on a pointer to a class when that pointer is null. That's dereferencing a null pointer. Sometimes we'll even land inside one of these methods, and it'll say that this is null, which is really confusing, but the basic idea is the same. You can't do that. So somewhere along the lines, it looks like I forgot to initialize my player in the constructor of the class. Oops, not here, there. So now that we've initialized player and set them equal to valid memory, that should be just fine. As an extra fun bonus, I'm actually going to delete player, which is going to free the memory before I use it to see what happens. This will probably get us a much more interesting crash. In this case, now we actually see bad access, but instead of seeing code or address equal to 0, it just says GPL fault, which usually means general protection fault. If I were to print out player, instead of getting null, we would get something wild. But essentially, we don't know that's wild because before I called delete, player was indeed a valid pointer. So if I try to dereference him to see what's inside of him, we'll actually get inside and see a bunch of values that don't make any sense. This is one of the reasons why this particular kind of crash, dereferencing a wild or no longer valid pointer, is so dangerous. Because it's really hard to see by looking at this that the damn thing is invalid. I mean, as far as I can tell, these values don't make any sense, but it's really hard for me to determine why they don't make any sense and what went wrong. This is more of an advanced version of the same crash. So I just wanted to print that out. Really, the only way to figure out what went wrong is to decipher through your code and say, hey, did I delete this thing? Has this been recently freed? And then if you figure out that's what occurred, then you'll know that that's how to get to the bottom of that crash. That's a hard one. I just figured I'd show it to you guys. Oh, we saw something for a second and then immediately crashed. That's sad. In this particular case, it looks like we were trying to make one of the enemies in the game shoot. So, address is 0x50, which is really close to 0, but not close enough for me to really say I'm not sure if it's a null pointer access problem. Code is 1, bad access, so it's some kind of invalid pointer, and there's really no other code or functions besides update logic, so we don't know if we made it inside of the shoot function or not. So let's get a look at some of the variables here. Let's see what this is. This is the pointer to this game loop, which is probably valid when this is being called. I'm just going to assume that. Let's get a look at enemies. Enemies is a C++ vector, which is basically a high-level array. But you can see the size is 0 and there's nothing in it. So obviously you can't access the 10th element of an array that's completely empty. So that's going outside the bounds of an array again, and essentially this line here makes no sense. I put this in here to kind of see what would happen, and of course it crashed. Oh, we're moving. No, we're dead. All right, another thing seemingly went wrong here. What happened this time? It's funny how calm I am right now, because if this was crashing and I was actually interested in showing this thing working, or I was actually working on it, I probably would be more frustrated. This particular crash actually happened to me in a different version in this program when I was working on it. Exe arithmetic essentially usually means there's some kind of a problem with floating point arithmetic, and here when it says div, that really clues me in that we probably divided by 0. not necessarily floating point, it could be integer arithmetic as well. In this particular case, it's pretty obvious to me that if I were to even read the code up there, but also print it out, that enemy reduce frequency is actually 0, when in reality I meant for it to be 60 when I wrote this, which basically means every 60 frames go inside this code and do what's inside here. It's also important to remember that moduloing by 0 is the same as dividing by 0, which will cause your program to crash. It's a common way to run into this situation. Another thing I want to say before it escapes my mind is that these particular exe codes or whatever are actually specific to Mac OS. On Windows, you'll get something completely different, and on Linux, you'll get something completely different. So it really comes down to which operating system you're using the most. Like Linux sometimes will call bad access segmentation faults. And on Windows, I don't know what the heck it calls them, but I'm used to seeing them a lot when I was working on Virtual Studio, so I definitely would recognize it when I saw them. So I went ahead and fixed this, and I'm going to move this on, and let's see what happens now. It looks like everything's fine. Oh, maybe not. I went to hit the space bar to shoot, and I can see here that once again, we have a crash. This says bad access. And we are all the way down here in some template code. Again, when I see template code, unless I really think it helps, I just immediately jump out of any kind of system library code into the deepest function that I wrote, my code that crashed. So this is the lowest that we've possibly gotten. Let's look at the arguments here. So we've said x, y, that looks valid, dy, valid, enemy. So everything in here is just ints and floats. It's very hard to screw those up, especially when they're not pointers. So that all looks valid. Let me get a look at the bullets array itself. It says could not read its memory. Whenever you're looking at essentially a member of a class, in this case bullets, if you cannot read its member or you cannot read its memory, that usually means the class itself is corrupt, or the pointer to the class itself is completely wrong. So in this case, the first thing I would probably do is get a look at this, and sure enough, this is null, which basically means that we called add bullet on a null pointer. Another way for a telltale sign to look at this is that this address B0 is close enough to 0. It might include me that I had a null pointer to reference. If I jump back up here to shoot, let me print out game loop here. Sure enough, game loop is a null pointer, so let's see who passed null to shoot. I did. So in reality here, I meant to pass a pointer to the game loop, in other words, this game loop to this function, so that essentially when I call player shoot, shoot has a reference to the game loop so that I can essentially call add bullet on the game loop. I did something very similar to this in another example I did on this channel, I'm pretty sure. So that's been fixed. I'm pretty sure that was the last one. So I'm pretty sure the game will actually run normally now. Oh, maybe not, actually. I think there was one other gotcha I put in here that didn't crash, which is actually kind of scary. So I was actually expecting this to crash, and I'm actually kind of, in a way, glad it didn't. Sometimes you can actually make mistakes in your program and they won't crash, and those are the scariest kinds, because in those cases, sometimes they'll crash, maybe 1 out of 100 times, maybe on a different computer that you can't access, and someone says your game doesn't work, and you say it does, and then you disagree. And this is one of the reasons why it's so useful to just test and do as much debugging as you possibly can on as many machines as you want to, or as many machines as possible. In this particular situation, text is a pointer to an STL texture, which is wild or uninitialized. In a lot of cases, it'll probably end up being null. If I were to put a breakpoint in here and actually run and land inside this function and print out text, it's actually a wild value, which is really surprising to me that when it gets to this line, it doesn't crash, but it doesn't. But essentially, it's doing something improper. It's probably corrupting memory somewhere else in the program, which is very scary. What I meant to do when I wrote this code was to set text equal to an STL texture from surface. I've noticed this in other cases where the STL library seems to have a lot of validation built into it. Passing null pointers as arguments to a lot of STL functions doesn't break it like one would expect. But it's a case where you, the programmer, really need to be careful to avoid these kind of situations so that they don't crop up. All right. Looks like my game is working properly now. I see my score label has appeared. The enemies are shooting. If I shoot too much, the gun overheats, which is what I wanted. So I'm going to show you guys one more example to round this video off. One other crash that I wanted to kind of show that could occur is really scary version of the crash, because it's the case where you can corrupt memory in a way so much that you actually corrupt other parts of your program, such that the OS can't tell that you went outside the bounds of an array, but your program will crash in random places and you won't know why. This particular function here is setting my tile map to random grass, setting certain parts of my tile map, random tiles, to the grass tile. When I tell it to essentially go between random values between 0 and 640 and 0 and 480 instead of the width of the tile map, which is only 20 by 15, you would expect the code to crash somewhere inside here. But what I actually found when I did this was, in some cases, the program will just work, like here. And in other cases, when I run it, same exact run, all I did was run the program twice in a row. It's actually saying it crashed inside SDL poll event, inside an unnamed symbol, which essentially means I don't have the access to the source code of STL. So it's saying that I had a null pointer crash, or at least something like that, inside SDL poll event. Now, what's so unusual about this is that the code that I changed had absolutely nothing to do with SDL poll event. It had nothing to do with this part of the program or this section of the code. But somehow, by me changing this code here, which essentially sets data inside a block of memory, and I essentially, by setting values in that block of memory past the end of that block to 1, I've essentially broken SDL in a completely different place of the program. This is probably the hardest kind of crash to debug. I've had things like this happen to me before by accident that have taken me hours to figure out when I, even at my current experience level. And when I was younger, there were times when I just spent, a whole day and I just went and figure it out. So in cases where you have crashes that just defy all logic and make no sense, usually it's good to go back to the drawing board and say, hey, did I do something really crazy somewhere recently? This is another reason why it's good to use source control systems like Git, or maybe just making copies or backups of your code so you can go back and march forward and say, what was the change I made that caused this thing to completely break? This is essentially the kind of crashes that C and C++ programmers really fear the most, because they're just so silent and so hard to find. So essentially, by putting this back, it will fix this crash in a completely random different area of the program. And I've actually ran that particular crash multiple times before and actually had the program crash in about 4 or 5 different unrelated places. So that's the one I wanted to show you last, because that's probably the scariest. So I know I covered a lot of really crazy stuff in this video today, and some of it might be a little too much to take in all at once, but I really wanted to kind of at least explain my thought process and how I think when I'm debugging and fixing crashes and fixing mistakes in code. So I hope this was useful. I hope you all had a happy new year, and goodbye.